Section 1. Introduction. In this introduction, we discuss the recent progress in large language models, LLMs, and their impact on the field of natural language processing, NLP. These models, known for their extensive training data and numerous parameters, are highly effective in various tasks through zero-shot or few-shot in-context learning, showcasing their impressive adaptability. In the realm of information retrieval, IR, LLMs have also brought about significant advancements. Many studies have explored the integration of LLMs into a variety of IR tasks. However, it's interesting to note that LLMs have not consistently outperformed smaller models in IR tasks, which goes against our initial expectations. This inconsistency could be due to the complexity of IR-specific concepts like queries, relevance, and user intent, which are not commonly found in natural language texts and are inherently difficult to understand. At the same time, the concept of instruction tuning has emerged as a key method to improve the abilities and controllability of LLMs. Models that have been fine-tuned with instructions have shown impressive adaptability to new tasks without prior exposure. Despite the availability of many instruction tuning datasets, there is still a gap in their applicability to IR tasks. This lack of targeted datasets for IR adds to the challenges of effectively applying LLMs in this field. To address this gap, we have developed a new instruction tuning dataset for search, INTERS. This dataset is specifically designed to enhance the search capabilities of LLMs. We focus on three key aspects common in various search-related tasks: understanding queries, understanding documents, and understanding the relationship between queries and documents. We have collected 43 datasets covering 20 distinct search-related tasks. For each task, we have manually created a task description and 12 unique templates. These templates serve as a foundation for generating both zero-shot and few-shot data examples. We then mix all the data examples to construct INTERS. We have conducted experiments by fine-tuning several open-sourced LLMs using the INTERS dataset. The results show that INTERS consistently improves the performance of LLMs of different sizes across a range of search tasks. This improvement is observed not only in tasks that are directly learned in the training data, in domain, but also in tasks that are unseen in the training set, out of domain. Furthermore, we have delved into more nuanced aspects of model training and adaptation. Our experiments examined the impact of different instruction designs on the LLM's performance. We also investigated the role of data volume, considering how the quantity of training data influences the model's learning and generalization capabilities. Additionally, we pay attention to the effectiveness of few-shot examples, assessing how in-context learning can aid in adaptation to new tasks. Our work contributes in three ways. 1. We analyze and categorize existing search tasks into three groups: understanding queries, understanding documents, and understanding the relationship between queries and documents. This classification provides a structured approach to addressing the diverse aspects of search tasks and forms the basis for targeted model training and improvement. 2. We collect a new instruction tuning set INTERS, specifically designed for enhancing search tasks. This dataset is comprehensive, containing data from 20 search-related tasks and integrating 43 widely used datasets. The diversity and richness of INTERS are further ensured through the use of manually written templates and task descriptions. 3. We conduct a series of experiments to validate the effectiveness of applying instruction tuning to improve LLM's searchability. We also include an in-depth analysis of different settings and configurations. This thorough analysis contributes to a deeper understanding of the factors that enhance LLM's effectiveness in search-related tasks. In the next section, we discuss the use of large language models for information retrieval. LLMs have a remarkable capacity for language understanding, making them highly valuable in understanding user queries and documents. Therefore, many researchers have explored applying LLMs to IR tasks. Existing studies can be roughly divided into two groups. The first group of methods uses LLMs to enhance IR components. For example, LLMs can be used as query rewriters to understand user search intent more accurately, thereby reformulating original queries into more effective ones. LLMs can also be applied to model the relationship between queries and documents for tasks like document ranking. The other group of methods treats LLMs as search agents to accomplish a range of search tasks. A notable method is WebGPT, which uses imitation learning to teach an LLM, i.e., GPT-3, to use search engines and answer questions like a human. Different from existing studies, our research focuses on using instruction tuning to improve the overall performance of LLMs on various search tasks. This involves refining the model's abilities to interpret and respond to search-related instructions more effectively, thereby improving their utility in complex IR scenarios. Section Summary. Recent advancements in large language models, LLMs, have had a significant impact on natural language processing, NLP, and information retrieval, IR. However, LLMs have not consistently outperformed smaller models in IR tasks, possibly due to the complexity of IR-specific concepts. To address this, we introduce a new dataset called INTERS, designed to enhance the search capabilities of LLMs by focusing on query understanding, document understanding, and the relationship between queries and documents. Experimental results show that INTERS consistently improves the performance of LLMs across various search tasks, including both in-domain and out-of-domain tasks. Additionally, we conduct experiments to analyze the impact of different instruction designs, data volume, and few-shot examples on LLM performance, providing valuable insights for optimizing LLMs in search-related tasks. Section: Instruction Tuning for Large Language Models. We're going to talk about a technique called instruction tuning for large language models, or LLMs. This method is all about fine-tuning these models using a set of examples that are written in everyday language. It's similar to other methods like supervised fine-tuning and multitask prompt training. The great thing about instruction tuning is that it not only improves the model's performance on tasks it's been trained on, but it also helps the model to handle new tasks it hasn't seen before. We're using this method to specifically improve how LLMs perform on search-related tasks. Our work is inspired by a study called FLAN, but we're focusing on search tasks rather than general language processing tasks. We'll show that instruction tuning is a great way to improve how LLMs perform on a variety of search tasks. Now, let's talk about how we use instruction tuning for search. This method has shown to be effective in helping LLMs respond to instructions. We train the models to carry out specific tasks based on the instructions we give them. One of the benefits of this approach is that, after we've fine-tuned the models, they can understand and carry out instructions for tasks they haven't learned before. But it's important to note that search tasks, which are the focus of our study, are quite different from typical language processing tasks. Search tasks are mainly about two things: queries and documents. So, we've divided our tasks and datasets into three categories: understanding queries, understanding documents, and understanding the relationship between queries and documents. We believe that tasks in these categories will help improve the model's ability to interpret queries, understand documents, and figure out how they're related. After we've chosen the datasets, we write templates for each one. We then create the final dataset, which we call INTERS, by fitting the data samples into these templates. Creating a comprehensive instruction tuning dataset that covers a wide range of tasks can be quite resource-intensive. To get around this, we've decided to convert existing datasets from the information retrieval research community into an instructional format. We've chosen tasks that fall under the categories of understanding queries, understanding documents, and understanding the relationship between queries and documents. In information retrieval, a query is a request for information that a user makes. It's usually made up of keywords, phrases, or questions. The goal of a query is to find relevant information from a retrieval system, like a search engine. The effectiveness of a query is measured by how well it reflects the user's intent and how well it retrieves the most relevant documents. Understanding the query is a critical part of making the retrieval process efficient and satisfying for the user. So, we've collected a group of tasks that deal with understanding queries to improve the model's ability to understand the semantics of queries and capture the user's search intent. We've considered 8 tasks in particular. The first task is query description, which involves describing the documents that might be relevant to a user's query. We've used 4 datasets for this task: Gov2, TREC Robust, and FIRE 08, 10-12. The second task is query expansion, which involves turning a short query into a longer, more detailed one while keeping the original search intent. We've used 7 datasets for this task: Gov2, TREC Robust, FIRE, Query 2 Doc, and TREC Web 09-14. The third task is query reformulation, which involves making user input queries more explicit and understandable for search engines. We've used several datasets for this task. The fourth task is query intent classification, which involves figuring out the type of intent behind a user's query. We've used 3 datasets for this task, including TREC Web 0914. The 5th task is query clarification, which involves clarifying unclear or ambiguous user queries. We've used several datasets for this task. The 6th task is query matching, which involves determining whether 2 queries or texts mean the same thing, even if they're expressed differently. We've used the MSRP dataset for this task. The 7th task is query subtopic generation, which involves identifying and presenting various aspects of the initial query. We've used the TREC Web 0914 dataset for this task. The 8th task is query suggestion, which involves analyzing a series of queries and associated search behaviors to understand the user's intent and predict the next likely query. We've used the AOL dataset for this task, even though it has been officially withdrawn, because it's the most commonly used dataset for query suggestion. Section Summary. Instruction tuning is a method used to fine-tune pre-trained large language models, LLMs, by training them on specific tasks based on provided instructions. This approach not only improves LLM's performance on the trained tasks but also enables them to generalize to new tasks. In this study, the focus is on using instruction tuning to enhance LLM's performance on search-related tasks, such as query understanding, document understanding, and query-document relationship understanding. Existing datasets from the information retrieval (IR) research community are converted into an instructional format to create a comprehensive instruction tuning dataset. Section 3.1.2 Document Understanding. In the field of information retrieval (IR), a document is any piece of information that can be fetched in response to a search query, like web pages in search engines. Understanding these documents is crucial for an IR system to interpret and comprehend their content and context. This understanding directly influences the effectiveness and accuracy of information retrieval. Better understanding of documents leads to improved search results, more efficient organization of information, and a more user-friendly retrieval process. To enhance this understanding, we focus on 4 tasks. 1. Fact verification. This task involves checking if a claim is supported or contradicted by the provided evidence. It requires a thorough analysis of the relationship between the claim and the evidence, ensuring there's enough information for a definitive judgment. This deep understanding helps search engines to better comprehend the documents, improving their ability to deliver accurate and relevant results. We use 3 datasets for this task. 2. Summarization. This task aims to create a brief summary of one or more lengthy documents, capturing all essential information while leaving out unnecessary details. The summary should accurately represent the content of the original documents without introducing any new information. This requires a deep understanding of the documents, which can significantly improve the performance of search engines by providing condensed, relevant content. We use 4 datasets for this task. 3. Reading comprehension. This task involves generating an answer to a question using information from a given context. It requires a deep understanding of the text's context and semantics, enabling search engines to more accurately rank the relevance of retrieved documents based on this nuanced comprehension. We use 6 datasets for this task, including Squad and MS Marco. 4. Conversational question answering. This task involves responding to a series of related questions based on a given context. As these questions might build upon shared information, some details may be implicitly understood rather than explicitly stated. By thoroughly understanding and analyzing this dialogue structure, search engines can enhance their interpretation of user queries and their connections to relevant documents, thereby improving result accuracy and relevance. We use 2 datasets for this task, including Quack. Understanding the relationship between a query and a document in IR involves determining how well the content of a document matches or satisfies the intent behind a user's query. This involves interpreting the query's semantics, context, and purpose, and then assessing the relevance of documents based on how closely they correspond to these aspects. It is the core task of information retrieval. In this category, we mainly consider the document re-ranking task. Document re-ranking involves rearranging a list of candidate documents according to their relevance to the user's query. The most relevant documents, those that best meet the user's information needs, are ranked highest. It's important to note that candidate documents are often obtained from upstream retrieval systems. Since language models, LLMs, cannot process a large number of documents directly, due to their length limit and high resource cost, we do not consider the retrieval task. We use the MS Marco passage re-ranking dataset and the datasets in the benchmark across multiple domains, such as biomedical, finance, and social media, which includes Touche 2020, Quora, and others. After determining the tasks and datasets we plan to use, we start to construct INTERS. The construction process can be divided into 4 steps. 1. Pre-processing. We download all datasets from publicly available resources, filter out unnecessary attributes and invalid data samples, and then convert them into the JSONL format for further processing. 2. Template collection. Following the design of FLON, we create 12 distinct templates for each dataset. These templates use natural language instructions to describe the specific task associated with each dataset. To improve the diversity of the templates, we integrate up to 2 inverse templates per dataset. For example, for the query expansion task, we include templates that prompt for simplifying a query. Additionally, to enhance the LLM's task comprehension, we provide detailed descriptions for each task. These task descriptions serve a dual purpose, offering a detailed understanding of the task's objectives and establishing a linkage among datasets under the same task. 3. Example generation. For each data sample, we use the corresponding task description and a randomly selected template to generate n-shot examples, where n is between 0 and 5 in our experiments. For few-shot examples, where n is greater than or equal to 1, we insert the n examples between the task description and the input, where the examples are separated by special tokens. All few-shot examples are randomly selected from the training set. To further improve the diversity of the training data, half of the few-shot examples are constructed using the same template as the current sample, while the rest are constructed by randomly selected templates. Moreover, to ensure that the few-shot examples are within the learnable scope of LLMs, we apply a length filter to exclude examples that exceed a predefined length threshold, 2048 tokens in our experiments. 4. Example mixture. To compile INTERS, we randomly select examples from our entire collection until we accumulate a total of 200,000 examples. This number is determined to strike a balance between efficacy and training costs. To balance the different sizes of datasets, we limit the number of training examples per dataset to 10,000 and adhere to an examples proportional mixing strategy with a mixing rate maximum of 5,000. Under this scheme, any dataset contributing more than 5,000 examples does not receive extra weighting for the additional samples, thus preventing the dominant influence from larger datasets. Section Summary. Document understanding and information retrieval, IR, is crucial for improving search results and organizing information effectively. Tasks like fact verification, summarization, reading comprehension, and conversational question answering enhance the capability of language models to understand documents, leading to more accurate and relevant search results. Query document relationship understanding involves assessing the relevance of documents to user queries, with document re-ranking being a core task. By re-ranking documents based on their relevance to the query, search engines can better satisfy user intent. Section 4 Experiments. In our study, we adjusted several open-source language learning models, LLMs, using our INTERS system and assessed their performance in various scenarios. We will make these adjusted models available to the public in due course. We used 4 different LLMs of varying sizes, from 1 billion to 7 billion parameters. The first, Falcon RW1B, is a language model developed by the Technology Innovation Institute. It was trained on 600 billion English language tokens and is used to study the effects of large language models and the impact of properly filtered and duplicate free web data on their properties. The second model, Minima 2-3B, is a new language model designed to set a new standard in compute performance on common benchmarks. It does this by distilling knowledge from a larger teacher language model, Llama 2-7B, using a data mixture of 126 billion tokens from various sources. The third model, Mistral 7B, is engineered for superior performance and efficiency. It uses mechanisms like grouped query attention and sliding window attention to outperform other language models in various benchmarks. The fourth model, Llama 2-7B, is trained on around 2 trillion tokens and has shown exceptional performance across multiple benchmark tests. It is widely used for LLM research. In our experiments, we found that the Llama 2 chat model performed slightly better than the Llama 2 base after fine-tuning. Therefore, we used Llama 2 Chat in our main experiments and further investigation. For all the models, we used their publicly available checkpoints on Hugging Face. We implemented the fine-tuning process using PyTorch and Colossal AI frameworks. To optimize memory usage and speed up training, we used DeepSpeed 0 Stage 2 and bfloat 16 mixed precision techniques. We also used flash attention to further improve training efficiency. The training was conducted with a batch size of 32, a learning rate of 0.00001, and a maximum length setting of 2048 tokens. All models were trained on 8 Tesla A100-40G GPUs. We set the hyperparameters based on empirical observations, as our main goal was to validate the effectiveness of INTERS. Comprehensive hyperparameter tuning was not within the scope of this study due to resource limitations. We first performed an in-domain evaluation to validate the effectiveness of instruction tuning on search tasks. In this experiment, we divided all data into training, validation, and test sets. The models were fine-tuned on the training set and evaluated on the test set. As all tasks and datasets were exposed to the models during training, we call it an in-domain evaluation. The results showed that after fine-tuning on INTERS, all models of various sizes significantly improved their performance. This demonstrates the effectiveness and broad applicability of instruction tuning in enhancing LLM search performance. We also observed that larger models generally performed better than smaller ones. For example, Llama 7B and Mistral 7B performed better than Minima 3B and Falcon 1B. Interestingly, in specific tasks such as query reformulation and summarization, larger models without fine-tuning even outperform the smaller models after fine-tuning. This confirms the inherent advantages of larger-scale parameters in model performance. However, in tasks such as query suggestion, the INTERS fine-tuned Minima model with 3 billion parameters outperformed other models with 7 billion parameters. This suggests that fine-tuning smaller models can be a cost-effective strategy for certain specific tasks. We also evaluated the models in out-of-domain scenarios. Instruction fine-tuned LLMs have shown remarkable zero-shot performance on unseen tasks. We also investigated the generalizability of the models after fine-tuning on INTERS. We considered 3 scenarios: group-level generalizability, task-level generalizability, and dataset-level generalizability. In group-level generalizability, we excluded an entire group of tasks from INTERS, fine-tuned the models on the remaining data, and tested them on all datasets. This experiment helped us understand how distinct groups of tasks relate to each other and contribute to overall model performance. In task-level generalizability, we removed specific tasks from INTERS, fine-tuned the models on the remaining data, and evaluated them on all datasets. The goal was to assess whether fine-tuned models can generalize to unseen tasks effectively. In dataset-level generalizability, we excluded several datasets from INTERS, fine-tuned the models on the remaining data, and tested them on all datasets. This experiment aimed to evaluate the fine-tuned model's ability to generalize to unseen datasets within the scope of learned tasks. From the results, we found that models fine-tuned with the full INTERS outperformed those trained on the ablated datasets. This verifies the efficacy of comprehensive fine-tuning in improving search task performance. We also observed that models trained on a subset of tasks still surpassed the performance of the untrained models. This indicates that the different task groups are effectively complementary. We also found that the model can exhibit task-level generalization. For instance, models fine-tuned without the query intent classification task still outperformed the untrained one in this task. This implies that knowledge learned from other search tasks is helpful for understanding query intent. Finally, we found that some datasets are difficult for knowledge transfer from other datasets. We also noticed that removing certain datasets from training leads to improved performance on other datasets, highlighting the complex relationship between different datasets. This suggests a need for further exploration into the optimal combination of datasets for instruction tuning. Section Summary. In this section, the authors describe the experiments conducted using different backbone models, ranging from 1B to 7B parameters, which were fine-tuned on their INTERS dataset. They found that larger models generally performed better than smaller ones, but fine-tuning smaller models can be a cost-effective strategy for specific tasks. They also evaluated the generalizability of the fine-tuned models on unseen tasks and datasets, and found that the models exhibited task-level and dataset-level generalization, indicating that they can be effectively applied to other search tasks. Section 5. Further analysis. In this section, we delve deeper into our analysis by conducting a series of experiments to understand the effects of different settings in our INTERS system. We use the Llama 2 Chat 7B model for these experiments and assess its performance in a specific setting. Firstly, we look at the impact of task descriptions. In INTERS, each task comes with a detailed description, which is designed to improve the model's comprehension of the task and establish links between datasets under the same task. To test its effectiveness, we ran an experiment where we removed these descriptions from our dataset. The results, as shown in the table, indicate that task descriptions significantly enhance the model's performance across most datasets, whether or not they have been fine-tuned. This supports our theory that detailed task descriptions can help the model understand the tasks better. Moreover, these descriptions seem to boost the instruction tuning process, leading to substantial improvements in some cases, such as a 77.5% performance improvement on a particular task. We believe that these task descriptions not only clarify individual tasks but also promote more effective knowledge transfer across different datasets. Next, we compare our INTERS with FLAN, a commonly used dataset for fine-tuning language models on natural language tasks. Given the larger size of FLAN, we randomly selected 200,000 data examples from it for a fair comparison. To ensure fairness, we also removed the search-related tasks from INTERS for comparison, as FLAN does not include these tasks. The results show that both FLAN and INTERS can enhance language model performance on the three tasks, proving the effectiveness of instruction tuning in unlocking the potential of language models for search tasks. Notably, INTERS yields a more substantial improvement in search tasks, particularly in re-ranking tasks. This aligns with our expectation as INTERS is specifically designed for search tasks. However, training on FLAN achieves better performance on the fact verification task, possibly because this task is very similar to other natural language processing tasks included in FLAN. In the construction of INTERS, we developed 12 distinct templates for each dataset to guide the models in task comprehension. We studied the influence of these templates on model performance by comparing the performance when training with or without these templates. The results show that the model performs worse without these templates, indicating the importance of instructional templates in task learning. We also examined the few-shot performance of the language models fine-tuned on INTERS, given that INTERS comprises a mix of zero-shot and few-shot. The results show that few-shot examples consistently improve performance across all datasets, compared to zero-shot INTERS. Few-shot examples are particularly beneficial in tasks with complex output spaces, such as reading comprehension, potentially because these examples help the model better understand the task and output format. Lastly, we explored the impact of the volume of training data. We conducted experiments using only 25% and 50% of the data sampled from INTERS for fine-tuning. We also investigated the effects of task-specific data volumes by doubling the data for tasks in the Query Document Relationship Understanding group. The results show that increasing the volume of instructional data generally enhances model performance. However, the sensitivity to data volume varies across tasks. For instance, the query reformulation task shows consistent performance across data volumes, possibly because this task requires straightforward modifications to the original query, which language models can easily learn. On the other hand, increasing the volume of re-ranking data leads to improved performance in re-ranking tasks but influences other tasks like summarization. This highlights the need for further research to optimize the mix and volume of instructional data for diverse tasks.